inviting me. And the topic, you see, the topic is statistical inference. You don't have to write the details. I will definitely say this. And at any point, if you have any question, please stop me. Ask me any question related to this. Okay. Now, let's start with a pathetic experiment. I hope there are some others. And you see, this is a pathetic experiment. I don't know that how this experiment is already done. You see, the study of soothing effect of the mother's heartbeat on a newborn infant. Placed in the nursery for 4 days. Okay. So one group is called heartbeat group. That is exposed to the heartbeat of mothers. And another one I will call it heartless group. So not exposed to the sound of. So we have two groups. So group 1, heartbeat. Group 2, heartless. Is it clear? Two groups. Obviously, it's the result of this heartless. And data, statistics, generally based on data, and the data observations, weight change from the first day to the 4th day. Weight change. So weight gain or weight loss for the two groups. So data or observations. So here and here. So weight gain or weight loss. We want to know whether heartbeat group would gain more weight. What do you think? Heartbeat group would get more weight or not? Still there. This experiment and have data and statistical methods, techniques, and experiment. This heartbeat group would gain more weight. Really pathetic. But you have to do this. This is a statistical experiment. So what is your solution? How can you solve this problem? We have data, heartbeat group and heartless group. How can you check? How can you say anything in favor of this heartbeat group would get more weight? Any suggestion?
So we cannot suggest anything because after born initial 3 to 4 days, what loss will be there?
That is fine, but after 4 days, there may be some gain. So gain may be some loss, but it will be preferred if there is a gain relative to this. So we have two groups, and you are comparing these two groups. Okay? So if there is little gain, that will be preferred definitely. Okay? And generally, we are considering the same type of babies, because there are very weak babies, and that is for the heartbeat group, and another one, but that is not. This is more or less homogeneous. So how can you test?
Sir, we compared the day 1 weight with day 4 weight.
Yes, no, therefore, that is there. So it is actually weight day 4 minus weight
Day 1.
day 1. This is, so if it is positive, that means weight gain. If it is negative, weight loss. So here we have data, here we have data. So we have so how can we compare? The basis of this
Coefficient of variance. Coefficient of variance. You can calculate.
coefficient of variation. Okay. So data you have mean. You have mean.
Yes.
So okay, mean. Then variance. Then coefficient of variation, and so on. Then how can you compare? If the mean of this is larger than this, then you prefer this. What about variance?
Variance is less than you will prefer.
Variance is less. Okay, suppose the gain is very high and the variance is less. That means, so variance is less, you prefer or not?
The data are very close to the center. In that case, variance will be less.
But how can you compare? Because
For this
you see,
variation,
suppose this is low mean and here is high mean. This group has low mean, high mean. And this is the observations. The variance is very low. And here the variance is large. So which one would you prefer?
first one, the spread is
First one, because this mean is very low. It may be negative. So, how can I compare this?
So you have to check both the mean and the variance.
Yes, more mean and variance, that is okay, fine.
coefficient of variance.
But this is on the basis of the data and this is descriptive part. What is inference? That we want to study. How can we check? Okay, so you see the data. So this is your data. Heartbeat group 20 babies and 190, this is gain, 80 gain, minus 10 means loss for heartbeat group, and heartless group 36 babies. So here we have 20 babies, here we have 36 babies. Okay? Now you see, weight gain in the first group 70%. That's very good. Related to the other one, that's only 22%. Okay. So, on the basis of this data, we see some apparent effect of mother's heartbeat. Is it not true? 70% cases we see the weight, there is weight gain. And 22% cases there is weight gain of the heartless group. So which one would you prefer? First group. So there is some apparent effect of, so that is apparent effect of mother, that is based on this data. So where is influence? Statistical influence. How do you check? The first one, you see, one thing, you know R, package, use this R. So I have just written in this X is C 190, 80 means the observations are of X, that means first are 190, 80, 80, 75. Suppose you want to write the observation 2, 3, 4. How can you write? So suppose this is X1, this is X2, this is X3. So you write X as C. SAT is here, and I think we will explain it after the class. So this is the first observation, value. Second one, this is it clear? So there are, you see 20 babies, so we have 20 observations. 190, 80, 80, and so on. Similarly, for the Huntley's group, 36 babies, and the data, the observations are 140, so that is 1. So here we have x1, x2, x3 to x20, and here it is y1, y2 to y36. Okay? So let us see. So sample average gain. How can you find sample average gain? So average gain, this is average gain. So you have average means x1 plus x2 plus x20 by 2. This is sample mean. Okay? So how can you find? So this is 18 for the first group. It is 18. They didn't find it. In the second group, it is minus. So this is 18 and this is minus. Okay? 18 and minus 20. From this, it is really clear that, okay, but how can you test? What is the inference? Suppose it is not like this, 18 and minus 50. It is 18 and 17. Then do you think that it is still, we prefer, now it is very clear that the 18 minus 50 is very clear. But if it is 18 and 17,
We are go for the next one.
well, but you have this data only. Then, okay, let us see what is the technique, what is the statistical inference. Okay, so this difference is 68. So 18 minus 50 is 68. The question whether the difference is real or it occurred by chance. There is no effect of mother's heartbeat, just by chance, it is a statistical fluke. And that is the difference. So whether the effect is real, for that we want to check, we want to test for that statistically. Okay. So, statistician's solution. Test whether the effect is significant. There is really significant effect of mother's heartbeat. So first try to interpret the result. So effect is statistically significant if it is unlikely to have occurred by chance. It's not by chance. There is real effect. So our job, you see, what is parameter? Parameter is characteristic of population. And it remains fixed. It is just fixed. This population. Say, here is some hypothetical population is there. Some hypothetical population of heartbeat group and heartless group. And say, mean is the average of this group, some measure of central tendency, and say variance is measure of dispersion. Okay. Now we have two populations. So two populations means one is heartbeat population, another is heartless population. And suppose we consider two parameters. One parameter is mean of this group, population mean. This is a sample mean. So population mean of this group and population mean of this group. Two groups. We have, suppose we have two parameters. One is population mean for the first group, population mean for the second group. Okay, so average weight gain for the first group and average weight gain for the second group. But the problem is they are unknown. Suppose it is mu1 and it is mu2. These two are unknown. We are not aware of this full heartbeat group, full heartless group. So what is their mean? So mu1 and mu2, they are not known to us. So, for population, we draw a part. That is called sample. Okay. Then, after drawing a sample from the population, we focus on the characteristic of sample at hand. We have data. So this is heartbeat population. This is heartless population. Data, observation from this group of size 20. And here, size 36, we have this observation. And on the basis of this observation, we have to say something about their differences. This sample characteristic, based on this data observation, this is called statistic. This is called statistic. And a value which usually changes from one sample to another. Suppose you draw another observation, we have another observations from another hospital, then the observations may be different, and suppose you can calculate anything based on this, the sample characteristic may change or may not change. But population mean they are fixed. They are fixed, but it may or may not change. For example, sample mean. So you are considering the sample mean x1 plus x2 plus x20 by 20. If the observations are different, it may change or may not change. Is clear? So if you have a different sample, you have different observations and different statistic. So statistic may change. Now I just want to, so how can we write this using R? So just write XC1459. What is the meaning of this? The observations are 1, 4, 5 and 9. Okay? Then just write mean of X. Mean of X. So what should be the answer? What should be the answer?
1 plus 4 plus 5 plus 9 divided by 4.
So it is 4.7. Is it clear? So you just give this, the observation, see this 1, 2, 3, 4 or 1, 4, 5, 9 and this 4.75. So suppose your observations are like this 1, 4, 5, 9 and you want to use sample mean, then the sample mean is 4.75. And suppose you take another set of observations and this is like this, then what is mean of X? What is mean of X?
2 point something.
Okay, that's fine.
2.7.
2.7. But I mentioned that it usually changes. So statistic usually changes from one sample to another. Suppose you have this observations, then what is mean of X?
Sir, 4.75.
4.7. So we have different sets of observations, but sample mean remains same. So usually, so it may change or may not change. Is clear? Okay. So statistic may change, but parameter is fixed and unknown. Statistic parameter is fixed and unknown, but statistic may change from sample to sample. Then our objective to form an idea about the population based on the sum. So population is unknown, data known, observation. So on the basis of observation, we want to know something about the population. Okay? And this branch of statistics, this deals with drawing conclusions about the unknown population or population parameters from the known sample. And this branch is known as statistical inference. Is it clear? Population is unknown. We have a sample. We have a sample from this population, expecting that it is a representative of this population. And on the basis of this sample, on the basis of these observations, we want to case, we want to know, we want to draw conclusions about this unknown population or population parameters. Parameters are unknown but fixed. Is it clear? But difference between finite population and a hypothetical population. Here you see, this is a hypothetical population, so heartbeat group and heartless group, there may be, so we cannot observe this. The whole population is not, but finite population, you see, a well-defined collection of units, like the students of this BC9 engineering college. We know this is the whole population, this is the students. So this is a finite population. And hypothetical population is all potential customers for a product. So this is not known actually, this is hypothetical. And we want to frame this with a population using some model, some statistical model. You know this normal distribution, normal model, Gaussian models. So this model is like this. This is like mean and this one, this variation. So this is, usually we model this. So this is hypothetical population. And mean and variance of hypothetical populations are the measure of central tendency, measure of variability or dispersion. For this heartbeat group, this mu1 is the population mean. So suppose there is a model, the statistical model, and some population, and its mean is mu1. Which is the mu2 for this group, heartless group. This is mu2. Okay? So, is it clear? So, hypothetical and finite means you know this is a group. You know these are the possibilities. You can identify this. But it is difficult to find this heartless group. So, because you have to go there and the whole population that is not known. Okay? Next, you are taking a random sample. So, random sample means equal chance of being included in the sample. So, anyone has equal chance of being included in the sample. And to know the statistic and its sampling distribution. So, you have a statistic and its probability distribution is called sampling distribution of the statistic. I just explained this. So suppose you have this observation. If you have another set, another form of the statistic, so statistic here suppose here it is 18. Take another sample, so another observation, so another form. So there are several values of statistics, and the probability distribution of that is called sampling distribution of the statistic. And what is standard error? You have statistic may change, generally change, usually changes. So there is a variation of that statistic, and that variation, that standard deviation of the statistic is called standard error, and that is very important. So there is one statistic, say sample mean, say we generally write this as x bar. Sample mean, it changes and you have some distribution, you have some probability distribution. Its variance or standard deviation is called standard error. Its variation. Okay? And if its variation in the standard error is low, so variation of some statistic is low. What is the meaning of that?
Samples are uniform size.
There is no variation, they are more or less same. And if it is very close to that, so suppose, I will explain it. So small standard error means the sample statistic is likely to be closer to the population parameter. And large standard error means more uncertainty in the estimate. So if it is low, it is better. Okay. Now statistical inference, I have mentioned that there is a population, take a sample, conclusion based on sample, and you have conclusion based on sample on the there are three parts of statistical inference. One is called point estimation, interval estimation or generally set estimation, and another is testing of statistical hypothesis. I will explain point estimation, interval estimation, and testing of hypothesis. So for this example, we have two populations. One is heartbeat, another is heartbeat. Parameters are population average weight gain, statistic sample average weight gain. So point estimation. So suppose this is mu1, this is for heartbeat group, this is the population mean. Okay? How would you estimate this? Any suggestion? Population mean, you have data, observations like x1, x2, x20. So how to estimate this? Population mean, any suggestion of estimate?
Sample mean.
Sample mean, very good. Sample mean. So population mean, you have data. Sample mean, suppose I want to estimate. So this is, suppose this is the population. So there is population mean weight of this, the persons in this room. Now we want to estimate that. I take a sample, say sample of size 5. I take the weights. And how can we estimate this population? This sample mean weight. And that is one type of estimate for this. And so you are estimating this mean by a point, by a value. When you are calculating x1 plus x2 plus x2, by 20, this is 18. This is a point. So estimate something by a point. So this is called point estimation. So let us see what is point estimation. And another is interval estimation. So first, point estimation. So we have data x1, x2, xn is here, x1 observation. So this is x1, n is the sample size. Theta is a parameter. Theta is parameter which is unknown but fixed. So what is that? A single number based on sample observation. A single number, a point. So T is estimator, and this probability, I have mentioned the T estimator or the statistic. Probability distribution of T means sampling distribution, and mean of T, you can standard error, you consider this one. So first one is, for example, this is sample mean. Population mean is theta and population standard deviation is sigma. So let me write this. Suppose this is mu and this is sigma or theta. Sorry. This is theta and this is sigma. So we estimate this theta by x bar. What is x bar? Sample mean. So let me write sample mean. Very good. Now it can be shown the sample mean is mean of this sample mean, the population mean of this sample mean. So how can you find the population mean of the sample mean? Because you have a sample, its sample mean. Again another sample, its sample mean. Another sample, its sample mean. Another sample mean. So mean of all these means. So that is the population mean. Or you have the distribution, the hypothetical distribution or sampling distribution of this x bar. Its mean is, it can be shown the original mean is theta, then its mean is also theta. And its standard, this is very important, that is variance is sigma squared by n. If it is, the standard deviation is sigma, its standard deviation is sigma by square root of n. Can anyone explain the meaning of this? Sigma divided by square root of n.
It's a variance.
So this is the standard error. What is the meaning of this?
Deviation of the
Standard deviation of the statistic or estimator, that is x bar. Initially, the standard deviation is sigma. Now it is sigma by square root of n, because it is based on sample size n. Is it alright? Okay. Now, can anyone explain? See, what is the meaning of this? That. So this is standard error. Standard error means standard error of this x bar is sigma by square root of n. I have mentioned that what is standard error? Standard deviation of this statistic or estimator. But what is the meaning of this? Can anyone explain
The variance of the sample,
this variation? Is like this.
So double or square, we have to, when we find out the variance of a sample in statistical, we have to squaring the value.
Squaring this value and dividing it. That is fine. But what is the intuitive or what is the feeling from this? What is the meaning of this? That is more important. I know that this is the most difficult session after lunch, but let us try to enjoy. What is the meaning of sigma by n?
The probability distribution.
This is definitely a probability distribution. Can anyone explain the difference between these two?
second one is leptogati.
Second one is
Leptogati. It is high.
this may be same. This may be same. That is true. But regarding the dispersion,
Dispersion is high in the first.
first one dispersion is high, and second one
Low.
low. And suppose This is the true value of the mean. So here it is true value of the mean, and this is the distribution of, say, x bar. Which one would you prefer? Second one? Why? But why?
Variance is less.
Variance is why?
It's close to
And then
Because it's very close to population mean.
close to
that
the
means
population.
very good. That means here observations may be here, maybe here, and here it is very close to this. So if it is variance is very low, that means if our observation is x bar, there is very low chance that it is far from mean. Okay? Now explain. What is the meaning of sigma by 10? Standard error of x bar based on sample of size n is sigma by 10. What is the meaning of this? If n is 9, then it is
3 to sigma of 3.
then it is
Sigma by 100.
so which one is less?
Second one is
Sigma by 100. Now, what is the meaning of this?
if the size
Higher
If the
the population size,
Sample.
higher
N
the sample size, higher the sample size, the standard error will start reducing.
And that means you have data, more and more information. And then
So
If
it
the
can be said
population
this is
is
also
high,
higher
then
the
the-
sample size is close, becoming close to the population size. So that's why it's
very good, and that is the reason. That is the reason. If n goes to, in terms of mathematics, I have had
Limit-
several
limit-
mathematics
limit n
students,
tends to-
n tending to infinity, this goes to 0.
0.
yeah.
So if n is very large, this is very small.
Zero.
And very small means
The value.
it's like this, and our x bar, and another thing is very important, that its mean is theta. Mean of this x bar is theta. Suppose mean of this x bar is this, theta plus 1, and it is very close, then it is not meaningful. It is very close to theta plus 1, and theta is here. So,
There will be a skewed one.
yes, and for that, it is not close to theta, but it is close to theta plus 1. So that is also very important. So this is the difference between, this is precision. And it is, the expected, this mean of this is theta, this is accuracy, the difference between the estimate and the parameter. Is it alright? Okay, so as n increases, variance decreases, or standard error decreases, error decreases. Clear? Suppose we have data on the basis of 2 observations. It's not meaningful. If it is based on 20 or 30 observations, we have more and more data, more and more information of this hypothetical population. Is it clear? And the beauty of normal distribution is, if the original distribution is normal with mean mu and variance sigma square, then the probability distribution of x bar, that is called sampling distribution, that is also normal. And mean same theta and variance sigma square by n. Original theta sigma square, here theta sigma square by n. So that is the beauty of this x bar. The same, this start with normal, it is still normal. Another very important theorem in statistics, I just want to mention that is called central limit theorem. That is, x1, x2, xn, this is may not be normal with some mean and some sigma square, then the standardized value approximately for large n, that is also normal. So normal distribution is really normal. Okay, so generally we prefer normal and we consider our testing problem or estimation problem using that assumption that hypothetical population is not normal. So this is point estimation. But this is really abnormal, it's not. Oh, fine. So you see this picture. So for different n, you see, initially the yellow one, this is the original, so n1, and then 0 is the original theta actually. And you see, it just looks like this. And if it is like this, the observations are got very close to this. And that is the beauty of particular normal distribution and the sample mean and its distribution. Okay? So that I have mentioned. Okay. Now another important thing is mean square error. So let me explain this. Suppose theta is the parameter, okay? Theta is unknown parameter. And we want to estimate this. Estimate by using say T estimator, some statistic. So, if T is theta, then this is excellent. If T is theta, theta is known, unknown, but T is known. We have observed value of this. So, what is the meaning of this? What is the meaning of this? T minus theta. That means theta is the true value and T is the estimate. So this is error. Error in estimation. Okay? Error in estimation. But if we take the average of this, sometimes positive, sometimes negative, so we can't find the exact error. So it is better square or absolute value of this square. Okay? But you see, T is theta. It's not possible. You have several observations. So like say T is sample mean. T is sample mean. So you have observation x1, x2, x20, and then you calculate this T. To take another observation, another T, another T. Take average of this. So the population average, I like average of this. That is called mean squared error. Error squared mean. Mean squared error. Clear? Okay. So this is called mean squared error. Now you want to compare two estimator. So suppose for some distribution you are considering mean. Another one maybe median. Maybe there are several choices, median, say trimmed mean. So there are several estimators from some parameter. So how can you compare? Using this mean square error or square root of that. Root mean square error. It's clear? So for different theta, you calculate this and compare this. Okay? Compare this. So this is called mean square error to compare between several estimators. Which one is the best? Okay? So this is point estimation. And obviously a smaller MSE indicates that the estimator is more accurate. Error less accurate. So use either MSE or RMSE. Root. Now we move to point estimation. Any question from point estimation? Any question? Is it clear? Point estimation, we have parameter, unknown. You want to know that? We have data, we have sample. On the basis of that, calculate some estimator. To estimate, we have some feeling about that unknown parameter. And to measure, we have to calculate the standard error or this MSE of this. Yes, sure.
So if we don't know that, if that theta is unknown, then how can we calculate the error?
Very good. Excellent question. That is very important. So, you know that this is, so for that, this x bar, suppose this is x bar. So, x bar minus theta square and its mean. That is mean square error. And what is the meaning of that? Its meaning is, I have mentioned that mean of x bar is theta. Mean of x bar is theta. So this is nothing but variance of x bar. How can you calculate the variance? Observation minus mean whole square. Observation minus its mean whole square, and you take the average. That is your variance. So here, this is population variance. How can you calculate sample variance? X bar is sample mean. You calculate this difference. You calculate this difference. You calculate this difference. You calculate this difference. And then square, square, square.
Summation of that mean.
So this is sample average of deviation from the mean. And MSC, if it is a mean, then this, now theta is the mean of this. So this is nothing but the variance of this population variance. And what is the population variance of x bar? I have just mentioned. Is it alright? Now it is free from theta. It is free from theta. But still your question is excellent because sometimes it depends on theta. So we are not aware of the exact value of theta. Then we have MSE of theta for different theta values. For different theta values, so theta may be anything, any real number. So you can write or you can plot this MSE. So MSE of theta, MSE is a function of theta. So plot theta and MSE. Okay? And suppose your MSE is this and another MSE is this. Which one? This is 1, this is 2. Which one would you prefer? One is the lower one and the upper one is number 2. Which one would you prefer? Lower one, because MSE is lower. And this is not only lower, this is lower for every theta. Then it is the best. And that is the beauty of this x bar, and it is best for every theta. And you see, suppose it is like this, then it is very difficult to comment. Which one is better? Is it clear now? For different theta, you can plot this MSE and then compare. If it is completely below this line, then this is better. It's clear?
So can it be said that if we plot MSE versus theta,
Huh.
the line with a lower slope is better?
Slope means then it is a line. It may not be a line.
It will be curvilinear.
Yes, anything. So lower means here it may be like this. But the beauty is the MSE is always less than this. At any point theta, it is less than this. So it is better. But for some theta it is less, some theta so for some theta it is better, some theta it is better. You cannot say, okay, this is better.
There cannot be conclusive evidence.
Yes, no conclusive evidence is there. Is it clear? And for that, normal, this is sigma square by n. That means this is a constant. Whatever theta, this is a constant. This is a line. This is a line. Okay?
Sir, if sigma is unknown,
Sigma is unknown.
in that case we will replace this by capital S.
Yes, I have written there that if sigma is unknown, how can you find the standard error? So let me go. So sigma by root n is standard error. Sigma is, if sigma is known, then it's fine. If sigma is unknown, replace estimate of sigma, that is S, sample standard deviation by sigma, and that is an estimate of the standard error. So that is S by root n.
So,
Huh.
so my question is,
Yes.
if sigma is known, then if I use by mistake the capital S, what will happen?
Sigma is known?
Sigma is known, but still I am using capital S in the standard error.
Yes. This sample, this. So you can use that, but that is not for your observation. Your S is very different from sigma, then it is not good. Okay? But if sigma is known, you definitely use this sigma by 2. Generally sigma is not known. A hypothetical population sigma is known, it is very unusual, but if it is known from prior information or something like that, then you can definitely use that, you can use that sigma, or you estimate this sigma. If it is unknown, you estimate this sigma by S. Okay? Now I move to interval estimation. So here, what is point estimate? A single number. Okay, here I want to mention another thing. This misconception of this point, meaning of point estimation point. Suppose your theta is like mu sigma. So there are two parameters. Then, what is the estimator? Suggest some estimate of this.
X bar and
X bar and very good, X bar and S. So you see, this is mu and sigma is always positive. And how can we estimate this? X bar S. Suppose X bar is this and this height is S. So this is the point X bar S in two-dimensional plane. Still, that is the point. So mu sigma, two parameters. You want to estimate this by X bar S, and you plot this X bar S in two-dimensional plane. So this is a point. So estimate two parameters by this. So this is also a point. So this is a point estimate. Can you give an example where there are 5 parameters? Any distribution, you know? There are 5 parameters. Anyone? For non-statistician or non-mathematician, this is called bivariate norm. Mean, 2 means 2 variances, and another is called correlation between this. You have heard the name correlation?
Yes.
Correlation. So correlation between 2. So X, so pair X, Y. So its mean of this, mean standard deviation of this, mean of this, standard deviation, 4 parameters, and correlation between this. So 5 parameters. Then you have 5 parameters. You have 5. The statistic is 5. So this is a 5-dimensional plane, and that is also a point in the 5-dimensional plane. So it's a point.
So this is a hyperplane.
No.
How to
So
find?
you see, this is a point.
Yes, sir.
And if it is 3-dimensional, so this is a point, say X bar, S, and anything more. That is a point. So this is, so estimate the parameter, and you see this mu sigma is a point into two dimensional space. And you are using estimate this point by a point. It's clear. So this is point estimation. Next one is interval estimation. So what is that? So we have an interval. So we are not sure. Okay, so we estimate the parameter population mean theta by 2.5. We are not sure. Okay, so better so our theta is a population mean. And we estimate, point estimate is x bar. So suppose it is 2.5. So estimate this theta by 2.5. This is a point estimation. But okay, I am not sure. Then I can use an interval for this. It's called L and U. And L is based on the observation data. U is based on this observation. For example, it may be x bar minus say 1 and x bar plus 1. So what is the interval here? If x bar is this, what is the interval? 1.5 to 3.5. So so we are estimating theta not by a point but by an interval like 1 point. So theta is in between 1.5 to 3. So estimate theta by an interval. Okay? But an interval, x bar minus 1 plus 1. How can, so why not x bar minus half, x bar plus half? Why not x bar minus 15, x bar plus 15? What is the meaning of this interval? That is the important.
It relies on -1 to +1.
Which one?
Sir, yeah.
Why? Because your theta population mean lies between minus infinity to plus infinity. So,
what is the necessity of this type of concept? Where we know the point estimator?
if we know point estimation, it is just exactly the point estimation. This is another one. This is not only this theta exactly, but it has some range of this theta. It is not 2.5.
Yes, sir.
It is some range.
My question is, where we know the exact value, then why?
No, I am not. Theta is not known. Theta is unknown.
Yes.
I have to trace that. So you are tracing, you are estimating that theta by a point. But that point is not the true point. You are not sure. So you are mentioning not that exact point, but some interval, so that you have more flexibility about estimating this theta. Theta may be from 1.5 to 3.5. Okay? Not exact value, but this is another form of estimation. Just exact some point, but some interval. Is it alright? But the question is, how do we choose this L and U? That is very important. So L and U depend on observations, data. Is it alright? So you have data. On the basis of, you calculate it like this. X bar minus 1. You have observation x1, x2, xn. Calculate sample mean. It's minus 1, plus 1, and this is our interval. Okay.
So that means this lies on -infinity to +infinity or -1 to +1.
Which one? Theta. Theta is the population mean. It's like between -infinity plus 1. So L and U are computable from the sample. Now, what is confidence interval? It's not only interval. Some confidence statement should be there. What is that? The chance that theta lies between L and U is greater than equal to 1 minus alpha. Suppose your alpha is 0.05. I write this statement. L. Can I write L x1, x2, xn? Is it alright? It is based on data, based on observation. x1, x2, xn, and you calculate x bar minus this. This is a function of x1, x2, xn. And here, this theta, x1, x2, xn, and that probability is greater than equal to 0.95. That means you want to trap theta. Theta is unknown. You want to trap theta by an interval. You want to trap theta by an interval, and the probability is at least 0.95. So this is called a 95% confidence interval. We are so confident that theta lies between this L and U with probability at least 0.95. Okay? So choose L, U such that the probability that theta lies between L and U is 0.95. But so these are one-sided, these are two-sided, this is one-sided, L to infinity minus infinity to U. You consider this observation, 2.1 to 3.2, and a 95% confidence interval for theta. This should be the statement, your statement, based on data. A 95% confidence interval for theta computed from the observed sample is 2.1 to 3.2. But you are not sure that theta is really in between 2.1 to 3.2. This is an estimation based on a sample. May not. What is the beauty? The beauty is, if you repeat this experiment, take another one, and in each case, you just see whether this LU really traps theta or not. You repeat it 1,000 times, 95% chance it traps theta. And that is the beauty of this statement, and that is the beauty of the definition of confidence interval. And let me show, and definitely you have shorter interval, if it is 2.1 to 2.2, this interval, with high confidence, then theta is very close to 2.1. Shorter interval, better. Is it clear? Shorter interval, better. So you see this picture. So this is very important picture to know what is confidence interval. You see, the first one, the lower one is L, based on this data, and the second one, so first you take a sample, the first sample, on the basis of first sample, calculate L and U, and the red one is C5. So the original value of theta is 5. Okay? What about the first one? It traps the lower one L, upper one U. It traps. Second one, it traps. Third one, fourth, fifth. Which one?
After
After
30,
T.
after simulation of 30, that one doesn't travel.
That's one.
After
So, yes. So if you repeat this experiment, say 1,000, 10,000 times, then 5% times it may miss. But you are not sure your data whether it misses or not, because that is the beauty of statistics, and for that I am here. So you are completely unaware of the true theta. Theta is completely unknown. You have observations, and on the basis of observation you have to estimate that theta by point or an interval. So you see, so this LU, the construction of LU is very important. So choose LU such that the chance because L is a function of x1, x2, xn, so it has some probability distributions, and this probability is at least 0.95. So 95% chance that it traps, it really covers theta. And that is the beauty of that interval. Is it alright? So that is our LU, that is our confidence interval estimate of this parameter theta. Okay? This is after T plane. But, one second. Any question? You can ask any question, and please ask questions.
Sir, how to, sir, there is given that n equals to 2.1 and u equals to 3.2. Always the difference l minus u minus l is always same, or you have
No. It can be anything like this, you see. This is symmetry. X bar minus mu, x bar plus 1. It can be anything. X bar minus. If the distribution is symmetric, is normal, then you can write this as a symmetry. X bar minus something, x bar plus something. If it is not symmetric, like exponential distribution, then maybe different. X bar minus A, x bar plus B. The meaning is, if theta lies between these two, this probability is at least 0.9. So that is important. So this choice of AB depends on that this probability is, and it should be small. That is very important.
It's not.
And for symmetry, it is the best one. If it is symmetry, x bar minus something and then x bar plus same. Because symmetry, you see, this is symmetry, and so this is this minus this plus this is the maximum possible probability. Otherwise, to move here, right side or left side, then the probability is, the length would be, to get the same probability 0.95, the length would be more than. Okay?
Thank you, sir.
No, any question?
Sir,
No, I have not completed. Please don't say thank you now. Or do you want to say thank you now? It is fine, okay. Oh, 10 minutes? He is not ready? Okay. Then we can see some t-test. So here is some t-testing testing.
mean absolute error নিয়ে কি আমরা কোনো কাজ করি?
হ্যাঁ, করা যেতে পারে. It is definitely, you can see. So absolute value of t minus theta, you can see, definitely that is very important, because there are several, it is called loss function. Because between t and theta, t minus theta is error. You take absolute value, take square, or some different loss functions are there. But generally, we prefer t minus theta. Point estimation, clear? Interval estimation clear?
Yes.
Is it simply clear or crystal clear? It is not crystal clear. Then, okay. So third one, and probably the most important one. Maybe the confidence interval nowadays is very important idea. Use this confidence interval, and there is some link between this confidence interval and this testing of hypothesis. So statistical hypothesis testing. So hypothesis testing. To start with hypothesis. What is hypothesis? Hypothesis is just a statement. Statement about what? The unknown. Unknown means parameter. Very good. So unknown. So unknown thing is population or population parameter. It is just a step, which has to be verified with the help of sample observations. Okay. So we have data. Point estimation. Theta is unknown parameter. We estimate theta by a point. Okay, 2.3. Interval estimation. Estimate theta by an interval, 2.3, 2.1 to 2.5. For testing of hypothesis, This is a statement about theta, unknown parameter. Okay? Theta is 2. This is the hypothesis. Okay? This is a statement about population parameter. So in a heartbeat example, we have 2 parameters. I just say, ignoring this variance, 2 average weight gains. One for heartbeat, mu1, and another mu2 for heartless. Suggest one statement about these parameters.
They are equal.
They are equal. Excellent choice. Because no change. It's a heartless. We are so heartless to frame this hypothesis. mu1 and mu2 are same. Any other hypothesis?
Not equal.
Not equal to is fine, but which one is important? Which one is important? This is heartbeat group's average weight gain. This
That one is greater than mu2.
mu1 is greater than
mu1 is greater than mu2. That should be the claim. Is it alright? So that is another important hypothesis. And that important hypothesis, that is the claim, and that is called alternative hypothesis. And the remaining one, as you mentioned, that there is no difference between mu1 and mu2. They are same. mu1 minus mu2 is 0. mu1 minus mu2 is null.
It's not
So
like
null hypothesis. So 2 populations. So hypothesis of no difference, null difference. 2 parameters, mu1, mu2, they are same. mu1 minus mu2 is null. So null hypothesis, no effect. Null hypothesis is based on the assumption that the apparent effect was actually due to chance. So you are taking observations from here. So they may be different. So their 2 averages may be same, but you are taking observation, a sample. So this sample may be different. That's due to chance. But this alternative is contradicts null. So heartbeat group would gain more weight. So you see, this is our claim, and the claim is alternative. So put your claim alternative part, and null one is no different, status quo. Okay? So test. So hypothesis is clear. It's just statement. There is one statement, mu1 and mu2 same. Another statement,
mu1 is not equal to
not equal to, or here it is important, mu1 is greater than mu2. So this is null. For null, so 0 is here, null. So this is mu1 and mu2 are same, and the alternative is mu1. This is very important. That is greater than, less than, or not equal to. So this is our claim that heartbeat group would gain more weight. That is our claim. That we want to check. That is our alternative hypothesis. Okay, now hypothesis is clear. Testing of hypothesis. So what is a test? So test is a rule by which either we reject null hypothesis or do not reject it. So we have to take decisions. So this is a game, H0 and H1. Either we reject H0, so we call the test is significant because this is our claim and we reject this. Or another one is do not sufficient evidence against H0. So do not reject it. Generally, do not write accept H0. It's better, do not reject H0. Because on the basis of data, it is not possible to support this claim. Okay? So either reject H0 in favor of H1 or do not reject H0. Is clear? And a test is a rule. Okay, if this is true, then reject. If this is not true, then do not reject. This is a rule. This is a test. So for heartbeat group, suppose this is our problem. What is that? For heartbeat group, what is the population mean? So suppose heartbeat group, what is the population mean? Mu1. So suppose our claim is for heartbeat group, the average gain is more than 20. This may be a good claim. That is for heartbeat group, it should be very high. So it is more than. So it should be in the alternative. This mu1 is more than 25. And here, this mu1 is 25. So this is null and this is very high. So for heartbeat group, it should be very high. So it is greater than 25. And that is our claim. And null hypothesis is mu1 is 25. Okay. So this is a problem. Now, what should, this is very important. So this is the basic thing of this testing of hypothesis. And if it is clear, then everything will be clear. So this is the basic. Now please suggest any route where you reject H0 and do not reject H0. If we have data x1, x2, x20. For first group, we have data x1, x2. On the basis of this data, suggest a rule using which we can say, okay, if this happens, then you reject H0. Otherwise, do not reject H0. Please suggest. It should be from your side. Then it is clear for him. Suggest any rule. Parameter of interest is mu1. That is the population mean of the heartbeat group, which is unknown. It is a statement about the population parameter. So these are hypotheses, statistical hypotheses. Now to find a test, what should be your choice?
This mu1 is very close to the actual value.
Which one? But mu1 is unknown. How can you find mu1? When mu1 is nowhere.
25 is close, that is the difference between 25 and the value we are
That is alternative hypothesis, and mu1 is larger than 25. So you see, I'm drawing one figure. Suppose this is 25, okay? So suppose this is normal. And it is larger than 25, the figure is like this. The right side of this 25, okay? Is it clear? This is the null and this is alternative. Alternative distribution and this is null distribution. We mean this is 25 and here the mean is greater than 25. Now you have to frame one rule based on data. Suggest one rule. You are not aware of this mu1. mu1 is not known. But these two competitors, one is 25, another is greater than 25. You have data, x1, x2.
Yes, 25 is the mean we are claiming.
25 is the mean, okay?
And we can calculate the mean from the sample. So the
Very good, very good. So, first one, you want to calculate sample mean from the sample. So, this is your sample mean, x bar. So, you calculate x bar and your x bar is a representative of mu. So, mu1 is unknown. This is a point estimate. That is a representative. Now x bar is with you because you know x1, x2, xn, you know x bar. So x bar is there. Now, what is your strategy? What should be your strategy?
So based on the value of x bar, we will compare our null hypothesis.
Very good, excellent. Based on x bar, we compare. Based on the sample observations, we want to infer or you want to choose which one is better, H0 or H1. Now suggest.
Sir, maybe it's a mu H0 is better because the sample.
No, but you know only x bar. Suppose x bar is with you. So x bar, suppose x bar is 50. Then which one would you prefer?
Then we would take the alternative one
Alternative one, why?
because it is closer to the value 50.
X bar is really 50 and mu1 may be very close to 50. So if it is 50, then we prefer.
Yes.
Okay, very good. So then what should be the rejection region?
If it is less than 25,
Which one?
x bar.
X bar is less than 25, then you reject H0 in favor of this. Why?
Then we will reject hypothesis 1.
Hypothesis 1. So you reject H0 if X bar is large. Suppose X bar is 50. You prefer this one or this one?
Alternative.
Alternative. If X bar is 0, then you prefer which one?
None.
Null hypothesis.
So what should be the critical?
Error.
So what should be the critical region? X bar is
20.
Greater than 20.
greater than, may not be 25. X bar, if X bar is greater than some C, then you reject H0 because suppose mu1 is very large. What is the representative value of mu1? X bar. So X bar should be very large if this is true. So if X bar is greater than C, reject H0 in favor of H1. Alternatively, suppose your sample mean is very large. Then which one would you prefer? This one. So reject H0. And otherwise, do not reject H0. This should be the. And this is a statistic. And this statistic is used for testing purpose. So this X bar is called a test axis.
So how about
Okay.
the value of C?
This is an excellent question. Okay, let us see what is written here. Is it alright? Do not reject H0 otherwise. Otherwise means X bar is less than or equal to C. So this is called test statistic. This is called critical region, X bar greater than C, because this is the critical one, rejection of H0. And your question. Is your question last one? Choice of C. Okay. I definitely answer all the questions. I have prepared this. Choice of C, you can ask this question. I am very sure. Okay. You see, we have two types of errors. This is very important. Population is unknown, parameter unknown. We have data. So two types of errors. One is, you see, statistician's choice is what? Either reject H0 or do not reject. And nature's choice, that is completely unknown. One is H0 is true, Another H naught is false. Okay? Now, first one, reject H naught when H naught is true. H naught is true when you are rejecting it. This is an error. This is called type 1. Reject H naught when H naught is true. This is an error. And another one, H naught is false. Still, you do not reject it. H naught is false. You should reject it, but you are not rejecting it. That is another error. So two types of errors. And you see this case, H naught is false, reject H naught, very good, correct decision. And H naught is true, do not reject H naught, keep it, retain it. This is also a correct decision. So these two are errors. This is type 1 and this is type 2. Is it alright? Two errors. Ideal test. What should be the ideal test? A test where ideal test means what? No error. Error free. So, probability of chance of type 1 error is 0. Probability of type 2 error 0. Now, if this happens, there should not be any class of statistical inference where everything is 0. So, these are pathological cases. So, probability type 1 error is 0, type 2 error 0. You cannot minimize for fixed sample size, you cannot minimize this two probability of type 1 errors and type 2 errors simultaneously. This is not possible. So what is possible? Possible is control one and then try to minimize the second. So control this probability type 1 error. Alpha is a 0.05. It's called 5% level, control at 5% level. So probability type 1 error is very low. So consider one test whose probability type 1 error is very low, less than 0.05. Subject to that, try to find, so there are several tests, out of which all are of level alpha, level 0.05. Try to find that test for which the probability type 2 error is minimum. There is technique in statistics to find the best test. Okay? Now, what is your technique? Probability type 1 error less than equal to 0.05. Okay? And this is the answer of your question. Here, this x bar less than c. Try to find c such that probability type 1 error is 0.05.
0.5.
And from that equation, you can find. So let me write. So this is your critical region. What is type 1 error? Reject H naught. So this x bar greater than c. Under H naught. Under H naught, what is the value of theta? Value of mu 1? 25. So under 25, x bar has a distribution. From that, this is 0.05. From this equation, this is the equation, like left side you have equation on the basis of c, this is a function of c, and here this is 0.05, solve this, and you can find c. And that c is important, and that c is this c. So this c is really depends on alpha. If alpha is 0.05, this c. Is it clear, the choice of C? So that your probability of type 1 error is 0.05. Okay, is it clear? So this is called a level alpha test, level 0.05.
Sir, that means the alpha is a pre-assigned number.
Pre-assigned number. So if it is if you take it 0.01, no, generally we use these two values, this 0.01 and 0.05. Okay?
So that means this is a 0, 1, not a 0.1.
No. Alpha is a number in between that interval, 0 and 1.
Lies on 0 and 1.
Right? That's
So it's an open interval, na? We can select 0 and 1 also.
This is a very good question. You can find alpha 0, that is also possible in some cases. But in general, alpha is 0.05 and 0.01. These are two standard values of this. Alpha 0 means you are very strict. There is no chance of it, okay, no probability type 1 error. The probability type 1 is controlled less than
Sir, if the
1%.
value-
Some error should be there.
Sir, if the
So
value
give a
is
chance
alpha
to
equals
error.
1, if the value is alpha equals to 1, then
If alpha equal to 1, so there is no restriction. No restriction.
I guess
So you can take any test.
100%.
You can take any test whose probability type 1 error is always less than 1. Okay? There is some place where probability type 1 error is 1. That is also possible. You are strictly less than 1. There are several tests. But that is not the idea. Your probability of type 1 error should be very low. And then you control probability type 2. It should be very low. Is it alright? Okay. And this 1 minus type 2 error, that is correct decision, this is called tau. Okay, see this example. If you want to remember this type 1 error and type 2 error, for this criminal court trial, this is very important. You see, generally, you are guilty, that is our claim. Okay? Claim that you are guilty. Then you go to the court, and that is your alternative hypothesis. Claim. What is now? Not guilty. Okay? Now, what is type 1 error? You are not guilty. Reject H naught. So that is type 1 error. You have to control that. That is the rule. That is the rule. That probability should be controlled. Okay. So, this now hypothesis is not guilty unless there is convincing evidence against this. That is hypothesis testing. That is hypothesis testing. Okay? Reject H naught. So we feel that this reject H naught when H naught is true, you are very good. And you say, oh no, it's bogus. So this is serious. So control this. Control this, and subject to that restriction, this try to find those tests for which the set probability type error is actually being restricted. Okay? And this is type 1 error. His or she is actually not guilty, but jury announces him. And he reject H naught and conclude that H1 is substantiated because we're convincing evidence. And retain H naught, that is, do not reject H naught, to conclude that H1 fails to be substantiated. You have enough data. And type 2, what is type 2 error? What is type 2 error?
reject H1. Reject H1 and
Do not reject H naught when H1 is. Okay. So, do not reject H naught. So, do not reject H naught, but H1 is true. So, what is H1 is true? It's really guilty. But, you are free. It is also an error. Okay. So, test. The idea of test is clear. Testing of hypothesis. This is one-sided test. T, this x bar greater than something. Okay, if this is alternative, say H2 is mu1 less than 25, then what should be the critical region? What should be the critical region? If the alternative is this, then what should be the critical region? Here x bar greater than CR, so right-sided. If this is the alternative, then x bar is less than. If it is very low, prefer this. So reject h1. Okay? And if this mu1 is not equal to 25, then either it is very large or it is very small. So two-sided. Is it clear? So three types. Generally, this is one-sided and two-sided. This is right hand, left hand, and two-tailed test. So this is your question, and this is the answer. Choose C such that probability D greater than C. So let me see this distribution. So suppose this is the distribution, and you know the area under this distribution, that area is 1. And you choose P alpha. If it is right-sided, the area above P alpha, this is alpha. Okay? So this is so your region is x bar greater than x. Okay? So this is right side. And for left side it is this side. Now, for this. Okay, let me write this null hypothesis. What is the null hypothesis? You see the problem? So what is the problem?
Null hypothesis will be the suppose B bar is the guessed B bar, so B bar is equal to 2 lakhs.
But not B, not bar. Not bar. Bar means sample. You see, you cannot write x bar is 2.
No.
Because hypothesis statement about parameter, population. So hypothesis is your mean bill is 2. That is population bill. This is right. You cannot write it because x bar means what? Your sample mean. Sample mean is 2 or 2.5. That depends on your sample. You know that, but it is not known. Is it clear? H naught is a statement hypothesis of this statement about the parameter or population. So mean bill is 2. Okay? Is it all right? Now is the most important part. The alternative hypothesis. What is the alternative hypothesis? That
Greater than.
claim of the accountant. Guest bills have been increasing in recent months. The manager is very 2 lakhs. No, accountant is very strict. No, it is greater than 2 lakhs.
Less than.
Less than or greater than?
Less than.
Less than?
Less than 2.
Increasing in recent months. So what should be the claim? You see. So let us see. Think and state
The
what should.
accountant will go against the manager.
Yes, definitely, and that is our claim. Managers is this is 2, and the accountant says no. There is some problem with the manager. It's not 2.
You will try to prove that it is greater than
It
2.
should be more, and that is his claim. Claim of the accountant, and go to the statistician and check. This is the observations, and it is. So what is alternative? Claim. What is the claim? Greater than this. Okay. So alternative hypothesis is greater than this because that is the claim because it is increasing. In recent months, we see it's not strict account. And this is two-sided. This is one-sided. This is two-sided. You see. So you see this example. So accept the shipment or return the shipment to the supplier. The mean length is 2.3. So suppose So this is like some screw or this. So this is 2.3. So you have to put it here. If it is less, then it goes out.
Round.
And if it is more, it
It
cannot
will
fit.
not fit.
So two-sided alternative is important. Is it alright? So sometimes two-sided, sometimes one side. That is very important to frame the null and alternative. And alternative is the. So this is very important. Okay. What about that? This. What should be null? What should be alternative?
None is no stock out.
Yes. No change actually.
Change.
And
Alternative is reduced.
reduced. So this now hypothesis is proportion of stockouts before is equal the proportion of stockouts after. What should be the alternative?
The proportion of the stockouts is less than the proportion of stockout.
So is it clear? Alternative hypothesis. That is very important. You have to put alternative hypothesis when you are putting in the program, when you write the code R, you have to mention whether the alternative is greater or less. Otherwise, it's completely opposite. Okay. What about this? Has increased, increased. So it is greater than here. Okay. What about this? There are this type of problems, and it covers all the problems using this T test. After T is the T test. Let us see the T test. Okay, so this null hypothesis before is equal to the mean customer satisfaction score and is improved. Very good. This one has reduced. Excellent. This one
Alternative is improved. Now is no change in employee satisfaction.
is simple. Simple.
So,
Yes.
sir, please go to the previous slide.
This one. Oh, sir.
Sir, in the alternative, they want to change if there is a significant difference or not. So, in the alternative, it can be greater or lesser. It can
No,
be
because this, if there is a significant difference, in employee satisfaction before and after, there is satisfaction if it is better. If it is change, then it is not equal. If you think that there is, but because it is,
it's different, so it's not necessarily should be greater.
no, that is fine, but depends on the satisfaction. Then it depends. If it is satisfaction, then it should be more. I always that is dissatisfaction actually. But that depends on your choice. But that should be the alternative hypothesis. That is the important.
Yeah, that is the
and the null, it is
Now it's equal. I'm saying the alternative.
Yes. If it is both sides is important, then it is two-sided, like that. Screw. Okay, let us come to a very important concept of 430.
You continue, sir.
Continue? Yes. No. You are not authority to say this because they are ready to.
Yes.
Yes.
Okay, so please raise your hand if you don't want to know. Oh, you don't.
You change the
It is alternative. Okay. So I'll just.
You can
15
continue
minutes.
till 5. I need 30 minutes to demonstrate myself.
Okay.
Okay.
But this concept is very important. This given. You know, given. Very important concept. So this is our test statistic. And right right tail test or t greater than something is important, suppose. And reject H naught if t greater than c. And this is the definition of p-value. The probability t greater than equal to observed t under null hypothesis. So p-value is the probability of results like those actually observed or more extreme than those. So let me explain this. So your observed value of the test statistic t, if greater than this, we reject H. So this is our null, this is our rejection region. Observed t greater than equal to C alpha. How can you find C alpha? The probability type 1 and is alpha. So from there you can find C alpha. This is our technique. Okay. Now what is the p-value? So we have data. We can calculate observed t, and that t has some probability distribution. Calculate this probability. Observed t under null hypothesis, and this is called. So you see, you have data, you have observed. Now you are calculating the probability that your t is those actually observed, that is observed, and more extreme. And that probability is called p-value. Suppose the p-value is very low. What is the meaning? That if H0 is true, you have observed this and more extreme value, and this chance is very low, so your H0 may not be true. So your p-value is low, you reject H0. I will explain it again. So p-value is used to quantify the strength of evidence against null hypothesis. I will explain it. This is very important. So you see, this decision is p-value less than 0.05. You reject H0 and do not reject H0 otherwise. Can write p-value less than 0.05, the test is significant. Effect is significant. You see this 0.0 to 1. If it is less than 0.05 p-value, then you reject H0 and say this is significant, and it is greater than, do not reject H0. So let me explain it again. P-value less than 0.05. What is the meaning of this? Suppose H0 is true. You have this observed value. Chance of getting this observed value and more extreme, that chance is very low. That means probably your null hypothesis is not correct. So if it is not correct, reject H0. Reject H0. Okay? So reject, if p-value is low, reject H0. Okay? And if it is for right tail test, for left tail test,